All right, well, welcome everybody. Let's get into it. Homework 1, you've just submitted. That assignment you turned in to Blackboard before 11 o'clock. Homework 2 is available now. If you go to Blackboard, you'll see the second assignment. I have the PDF file of it posted. Remember that the way that these submissions work is that the link for submission vanishes right on the due date. And then that means you're also going to lose access to the PDF file. So if you want to have and retain a copy of the assignment description, you should save that locally onto your own PC. And then that way, when you're going back through the comments that the grader gives you on the homework, you'll be able to refer to the original question that was asked. So keep the PDF files if you want to understand what was originally asked in those problems. So the next assignment will be due a week from today, just with the first assignment, homework number 2, should be a single black and white PDF file that you upload to Blackboard. And if you have any questions or concerns about how to submit, then please let me know. Today we're going to talk about vapor pressure and hydrostatics. And if I remember correctly, I kept you a little bit late, maybe a couple of minutes late during our previous class lecture, so I think we may be able to wrap this one up a little early. I like to essentially always try and be respectful of your time and pay you back if I steal a minute or two here or there. But any questions related to the announcements or the course in general before we begin talking about the new material? All right. Please don't be shy about it. I think most of you have microphones automatically built into your laptop, and it's really efficient, and there's less of a lag if you just go ahead and ask your question rather than have to type it, and then there's ambiguity about what you meant. So feel free to interject if you do have a question as we move along. All right. So what are we looking at here? Looks like a picture of a coffee kettle, and you can see that it's being heated with gas underneath, and then there's steam on the top of the container, and so that's one clue that this water is pretty hot. But maybe the best clue that this water has been heated up to a certain temperature is that we can see bubbles in the water. Now, what are those bubbles? Is that air that's coming out of the water?
Water vapor.
Very good. That's right. It's water vapor. And so what has happened is that we have changed the phase or changed the state of the water. Water and liquids can exist in 3 different phases. They can exist as a solid, which is ice, and of course we know that the transition point between a solid and a liquid for water is 100 degrees Celsius. Sorry, 0 degrees Celsius. The transition point between liquid and vapor is 100 degrees Celsius, depending on the elevation you're at. And so what we're looking at here is we're looking at the liquid turning into water vapor. And so the little bubbles inside that haven't yet risen to the surface, these are bubbles of H2O gas. And so it's a gas and it's water vapors. So it's kind of interesting. We usually think of gases as being, nitrogen, oxygen, but the gas inside, beneath the water is H2O. It's water vapor. Now, I've already mentioned that at sea level, where we have one standard atmosphere of pressure, that water will boil at 100 degrees Celsius. And boiling is just another word for that transition between the liquid phase and the gas phase for water. At Mount Everest, if you're going to make a cup of tea at the top of the world, the highest mountain in the world, then the water is going to boil at 69 degrees Celsius. And so that cup of tea wouldn't nearly be as hot as a cup of tea that you could brew at sea level. And the reason for that is that as you go up through the atmosphere, there is less gas in the atmosphere. The surrounding atmospheric pressure is lower, and so that the water has to have less kinetic energy in order to escape into the vapor phase. And we'll talk all about that. But one thing I just want to point out is that the vapor pressure of the water depends on temperature. And so the temperature that water boils varies depending on elevation and pressure. And so maybe if you've ever baked a cake before from a box, one of those mixes that you can get in the grocery store, Duncan Hines or whatever, on the back of those boxes, oftentimes they'll have what are called the high altitude instructions. And the high altitude instructions are because of this fluid property, that water goes from a liquid to a vapor at different temperatures depending on what elevation you're at. So at a higher elevation, the water is going to evaporate out of your cake more easily than it would at a lower elevation. Because if you're going to bake your cake at 350 degrees, then the water is closer to the boiling point, or further beyond it, I guess we could say, further beyond the boiling point when you're at the high elevation. So vapor pressure is this fluid property that we're going to discuss today, and it's known as the pressure at which a liquid will boil. And when you increase the temperature, so goes the vapor pressure. And this data is taken from your textbook, and what we can see is that 100 degrees Celsius, the vapor pressure of water is 760 millimeters of mercury. And you may remember that 1 atmosphere is the same thing as 760 millimeters of mercury. There's a lot of different ways for us to express pressure. We can express pressure in PSI, millimeters of mercury, atmospheres, pascals, newtons per meter squared. And so, the value we use most often for standard pressure is 101.3 kilopascals. But another indication for that is 760 millimeters of mercury. And so what this says is that at 760 millimeters of mercury, which is equal to atmospheric pressure, that is where the pressure that the water exerts against the atmosphere, the water molecules that have been heated up, they're moving around really quickly and they're trying to escape from the water. They've got so much kinetic energy, they have enough kinetic energy that they can break through the barrier at the top of the liquid and they can go out into the atmosphere when the water has a temperature of 100 degrees Celsius. Now here's just a graphical representation of that same data. You can see that it's a nonlinear relationship, and that when you begin increasing the temperature beyond 60, 70, 80 degrees Celsius, that the curve is going up dramatically. The vapor pressure is increasing quite a lot. So this is the vapor pressure of water as a function of temperature. And what we say is that when the vapor pressure equals the atmospheric pressure, that's when boiling occurs. And so this word boiling, usually we associate that to mean with hot water. Most of your experience has been that when water is boiling, that means it's hot. And it's going to be really hot. You wouldn't want a pan of boiling water splashed into your face. It would burn you. But we're only thinking about our experiences with a standard pressure. If you have water inside of a reduced atmosphere, then the water will boil at a lower temperature. Stephen asks, if we're not given a temperature for a problem, at what pressure should be assumed? So you mean if we're talking about vapor pressure, you really do need to know the temperature. I mean, sometimes you could assume maybe it's just a room temperature. That's a pretty default assumption. If you don't have any other data, it would be 20 degrees Celsius. But for vapor pressure problems, most of the time I think you will see a temperature being specified. Now let's look at a video of water being boiled. And this is a little bit different. from how you've seen boiling water before. You've probably boiled pasta, but this video, the person is going to boil pasta without heating up the water. They're going to do something different to boil the pasta. Instead of heating up the water, they're going to suck the surrounding atmosphere away from the water so that there isn't there isn't air pushing down against the water, but the molecules of the liquid water are able to escape more freely into the sealed vacuum above it. So let's take a look at this. Okay, there we go. So if you have a liquid going into a gas, it cools off. It requires energy to do that. And so if you leave this running for a long time, actually what happens is that the liquid will freeze. It's boiling, but the temperature is gradually going lower and lower and lower because it's consuming kinetic energy to go into the gas phase. So it's kind of a complicated situation, but the main thing that I wanted to point out is just this concept of vapor pressure. And the vapor pressure, this water is probably at 20 degrees Celsius. And so if we go back to our data table, instead of heating the water to match atmospheric, instead of heating the water to 100 degrees Celsius, so that now the water has the same vapor pressure as the atmosphere, instead this demo shows that you can reduce the atmospheric pressure until it matches the vapor pressure for a certain temperature. So as long as the two things are equal, boiling will occur. As long as the vapor pressure and the atmospheric pressure match, boiling occurs. And so you can either raise the vapor pressure by heating the liquid, or you can lower the atmospheric pressure until it matches the liquid's vapor pressure at the lower temperature. All right. In the back of your book, there's an appendix table, table A5, and it has the vapor pressure for a variety of different temperatures that's provided. One thing I failed to mention on the previous slide is that even when the water is frozen, it still has some vapor pressure. And water does evaporate from ice. Very, very slowly, but it does evaporate from ice. In some of the far northern territories, like in Alaska and northern Canada, it's possible to wash your clothes inside the house and then put the wet clothes outside on a line, and they'll freeze, but the water will eventually evaporate, and that's the process of going directly from a solid to a gas is called sublimation. And so you can see that the vapor pressure of -10 degrees Celsius water is 2.1 millimeters of mercury. So it's not going to evaporate quickly, but it will still evaporate. All right, so we looked at the pasta boiling. Let's look at another manifestation of the vapor pressure of water. This video is taken in Canada. Yellowknife, Canada is one of the really cold parts in Canada. And what this person has is a tea kettle of boiling water, and they're just going to illustrate when you have really cold air, how quickly the water can go into the vapor phase if there's a large differential between the air temperature and the liquid temperature. But if the temperature gets down, you know, maybe -10 degrees Fahrenheit, then the water is going to evaporate really quickly. All right, now this is interesting, but it has applications that go beyond just kind of the gee whiz, throwing water into the air and boiling pasta at room temperature. You know, there's more to it than that. One of the really important engineering implications of vapor pressure is a process that's called cavitation. And we're going to talk about what cavitation is and some of the problems it can cause by looking at a case study of a dam in Russia. This is a dam that generates quite a lot of hydroelectricity in Russia. I'm not going to attempt to pronounce that because I don't speak Russian, but you can see the power lines coming off of this dam are kind of an indicator that it's an important source of electricity for the industry in that part of Russia. And this is a before photo. So before, that's ominous, right? There are generators built into the floor, and the way that the dam works is that water goes through these pipes and it moves at a very fast speed, and the difference in the elevation between the reservoir that's behind the dam and the water that is downstream of the dam, that elevation difference combined with the flow of the water creates a pressure and spins the turbine in these generators. So the spinning turbine is converted to electricity. It's hydroelectric power, and we have a lot of hydroelectric power in the United States as well. This is the after photo of that same location. And so the only thing that's, if you look at these tanks, the air oil tanks, here's the yellow stripe, the blue stripe. Okay, here it is, the yellow stripe, the blue stripe. We still have those tanks, they survived, but there's really been a lot of damage. It almost looks like maybe some sort of an explosion. What happened was that the water was moving so quickly through the penstock, which is the name of these pipes in a dam. They're called a penstock. That's what carries the water from the reservoir to the turbine. When water is moving at a really high velocity, then the pressure decreases. We'll talk about the details of that when we discuss the Bernoulli equation, but the Bernoulli equation just basically is a way of quantifying the relationship between increased velocity and decreased pressure. So the pressure of the water going through these penstock tubes became so low that it was lower than the vapor pressure of the liquid. So the water was moving so fast through those pipes. I guess it was maybe very rainy in the watershed upstream of the dam, so they had to pass a lot of water through the dam. And that dam had been in place for a long time, but this was a unique set of operating circumstances where I think they maybe had one of the turbines closed for maintenance, and so there wasn't water going through all of the penstocks. There was a greater amount of flow going through any single penstock than there had been before. And so the velocity was high, the pressure came down, and what happened is the water started to boil inside of that concrete tube. And it wasn't hot, it was boiling in the sense of there was an expansion of liquid water molecules into gaseous molecules. And so when that gas hit the generator, it can cause little shock waves as the gas bubbles collapse, and it can very gradually start to scour and erode both the concrete and the steel, and it became, I think, a real acute failure when the scour and erosion caused an imbalance in one of the fast spinning generators, and from it becoming imbalanced, it just ripped right up out of the floor and destroyed everything else. So the take-home lesson of this case study is that if the absolute pressure of the water falls below the vapor pressure, then cavitation will occur. And cavitation isn't just something that happens at dams in Russia. Cavitation is an effect that we see. The U.S. Navy is really concerned with cavitation because when you turn the propeller of a submarine or a ship very quickly, when you're accelerating that ship or submarine, then those little vapor bubbles will form on the edge of the propeller, and they can be very noisy. In the case of like a submarine, the noise of those bubbles being formed and then collapsing is enough to give away an otherwise silent submarine's location. Submarines are always trying to be very stealthy and quiet, not detected, and so if there's cavitation on the screw, then it can give away their location. So that's another application. Even in just ordinary situations like a municipal water network, we have to be aware and cautious about the effects of cavitation. Anytime you have a pump, you have to look at how much suction is on the upstream side of that pump, because if there's so much suction that the water pressure has fallen below the vapor pressure, then those little water vapor bubbles can form and can start to cause pitting and damage to the impeller inside of the pump. So we'll talk more about cavitation, especially when we get into hydraulic engineering. For those of you civil engineering students who will be with me next semester in CE 331, it's a calculation we have to do when we're performing hydraulic design. But it's important for mechanical and civil engineers alike. All right, so let's move now from cavitation and talk about determining how pressure changes as you go down through a liquid. Now, I told you in the lab, for those of you who are in the lab, I told you that a big part of the lab is to test equations and see how accurate they are. And this is one of the equations that is very accurate and also very important. So this is a model. This equation describes the way that the world works. That's what an equation or a model is it's a way of simplifying and describing reality. And what this equation says is that the change in pressure and the change in elevation go in opposite directions, and then the rate of change between the two is negative gamma. Now, gamma is the symbol that we use to describe the unit weight or specific weight of a fluid. Both of those terms are interchangeable, unit weight, specific weight. That is the 9810 newtons per meter cubed. So what this says is that if you go down through a fluid, that the pressure is increasing. So they go in opposite directions. The elevation is going to be measured according to some datum or a frame of reference. That's what a datum is. So this is our baseline. We're saying the bottom of the tank is where we're going to measure elevation. And if we go up through the tank, then the pressure decreases. If we go down through the tank, the pressure increases. That's the hydrostatic equation. And the rate that pressure changes is equal to gamma. Any questions so far about this idea? The question is, does the pressure increase linearly? And the answer is yes, it does. For every meter that you go down through water, the pressure increases 9810 newtons per meter squared. So 9.81 kilopascals is how much the pressure goes up. Now, if we go to the bottom of the ocean, you remember we talked about Challenger Deep at the bottom of the Mariana Trench and how the pressure is high enough there that the density increases a little bit. You know, in the extreme situations, it's no longer linear. It's increased a little bit just because the water has compressed and is more dense. But for all practical purposes, yes, it's a linear relationship between pressure change and elevation change. Good question, Gavin. Other questions? All right, so let's think about pressure. Go ahead.
Would the pressure also be affected if two liquids were in the system instead of just one?
If there's two what?
If there were two different fluids in the system.
Okay. That's a great question, and we have an example coming up that'll address that very point. For example, you know, what if there's oil floating on top of the water, right? That's the case that you kind of have in mind?
Yeah.
In a case like that, the pressure increase is linear, but we have to do it in steps. If we're trying to figure out how much the pressure increases between the oil layer and the water layer, we have to first of all go through the oil they'll have different gammas, you know, because the oil would be less dense than the water would. And so we can still apply this same equation. It's just that we have to break it up into segments and not go down through the liquid in a single step if there's different multiple fluids. All right. Talking about the units here. Okay, so dP, change in pressure, is newtons per meter squared. So if you've got your notes there, if you're taking notes in the margin of the lecture slides. Okay, write down dP equals newtons per meter squared. And dz is going to have units of meters. So if you have newtons per meter squared and divide it by meters, then that gives you newtons per meter cubed. And that is the same units as gamma. So the units do match up. This is a dimensionally homogeneous equation, meaning that the units on the left-hand side of the equation equal the units on the right-hand side of the equation. Fundamental equations like this, formulas that have their basis in the fundamental processes of physics, typically are dimensionally homogeneous. Empirical equations where we're just doing curve fitting based on observed data and the equation isn't so much generated by the foundational principles of physics, oftentimes those formulas aren't dimensionally homogeneous. But here, the left-hand side units and the right-hand side units are equal. All right, so if we have a fluid with a certain density and a specific unit weight, and it's constant through the fluid, and it will be constant unless we get down to some really incredible depths. The density doesn't change through a liquid, and it changes a little bit through a gas, but even up many thousands of meters into the atmosphere, it's still a linear relationship between elevation and pressure. So here's the hydrostatic equation that we saw before on the previous slide. And if we integrate that, then we get an expression for piezometric pressure. And so what piezometric pressure is saying is that you can measure the pressure plus the unit weight of the fluid multiplied by the elevation above the datum. We're going to define this as piezometric pressure. And what it's saying is that in a fluid like this tank of water from the previous slide, instead of just knowing what is the pressure at a certain point, sometimes it's important to know what's the pressure there and also how high above the datum is it. And so, we could measure maybe a certain point is 1 meter above the bottom of the tank, and then we also know the pressure there. The piezometric pressure is the combination of those two terms, the measured pressure intensity and gamma times z, which is a function of how high above the datum that point of interest is. So that's piezometric pressure. You can express piezometric pressure a different way if you divide each term by gamma. And so pressure divided by gamma plus z, that's piezometric head. So the hydrostatic equation allows us to choose two different points in a fluid and predict how the pressure and elevation is going to change in relation to those 2 points. So if you know in 2 locations the pressure and at one of them the elevation, then you can calculate the elevation of the second location. Any one of those terms can be an unknown. And so what I mean by that is if you have a tank like this, and let's say location 1 is 34 meters above a datum. And the datum can be the bottom of the tank. The datum could be sea level. In fact, the datum could even be the surface of the liquid. It doesn't matter what we're using as our basis point for measuring elevation, as long as we use that same basis point for both location 1 and location 2. As long as we're consistent, then it doesn't matter which is which. So let's assume that this tank is at sea level, and we want to know at location 2 what's the gauge pressure and also what's the absolute pressure. Remember on Tuesday we talked about the difference between gauge and absolute pressure. So if you don't remember, I'll refresh your memory as I show you the solution to this. But what I'd like you to do is try substituting the numbers into this formula. Hopefully you've got a calculator handy and a writing instrument so you can jot this down right there in the notes with you. But given P1, given Z1, and then if this is water, see at the bottom it says water, so that tells us the gamma is 9810 newtons per meter cubed. Solve for P2 using the formula. Let me bring the solution up onto the screen so we can compare. Peter confirms. All right. So our hydrostatic equation is here, and we're given a Z1 of 34 meters. The given gauge pressure P1 is 66,000 newtons per meter squared. And the problem statement said newtons per meter squared. It could have just as easily said pascals. Or if it said 66 kilonewtons per meter squared, then that would mean the same thing. But to put it into the formula, you need to put it into the units that are going to cancel out correctly. And so if it had said 66.0 kilonewtons per meter squared, then you'd need to change it to 66,000 newtons per meter squared, because you're going to be, as you can see later on, dividing by gamma. And to get the units to cancel out correctly, you can't have kilonewtons in the numerator and newtons in the denominator. So you need to be dimensionally consistent, and that's one of the reasons why I suggest it's really a good habit to get in to include the units anytime you are defining a variable or substituting it into a formula. All right, so let me change this back. All right. So if we look at the solution, I've rearranged algebraically to solve for the unknown. P2 is what we're trying to find. And so if we rearrange our original hydrostatic equation and solve for P2, then it's going to be P1 divided by gamma plus Z1 minus Z2, and then all of that multiplied by the unit weight of the liquid. And I'm doing this habit of writing the units, not just the numbers, and then also showing the intermediate steps. Don't just write the equation and then write the answer. You're going to get more partial credit when you make a mistake if you show the substitutions, because you're kind of providing more clues that you actually understood the material if you include the substitutions along the way. So in the end, the gauge pressure is 144 kilopascals. And gauge, remember, means the pressure relative to atmosphere being considered zero. So what gauge means is, if we're talking about gauge pressure, we assume that the water and the air have the same pressure at the surface. So we're saying the pressure is zero, and then it increases the further down we go. That's gauge pressure. Absolute pressure is when we say, well, actually, the Earth doesn't have zero pressure. I mean, it has zero pressure compared to itself, but compared to the vacuum of space, it has 101.325 kilopascals. And so the conversion between absolute pressure and gauge pressure is that we add the atmosphere's pressure on. And so if this is at sea level, then the atmospheric pressure is 101,325 pascals, and so the absolute pressure is 245,805 pascals. Did you get that one, Peter, too? Absolute pressure. All right. So be sure that when you have a homework problem, that take a look if it says gauge or absolute. Now, eventually, it'll just say, like, what is the pressure? And kind of the default typical assumption is that you're using atmospheric as the reference point. But we use absolute pressures for problems that include the gas laws. So I'll sometimes call this the full hydrostatic equation.
Can I see the solution again, please?
Yep.
Thank you.
All right. So So this formula, absolute pressure is gauge plus atmospheric. So if you knew gauge and you know P atmosphere, you can find the absolute pressure. The full hydrostatic equation is sometimes simplified into an abbreviated format. So delta P is delta H times gamma. And this abbreviated format is just saying what's the change in pressure between two locations. So rather than solving for P2 in direct terms, you're just finding how much the pressure changed. And so you may remember that this is the equation I used on the first day of class when we were doing that Challenger Deep problem. I said that the pressure at the bottom of the ocean was its depth multiplied by gamma. Now, by the way, the gamma for seawater is different from the gamma of regular water. If you look up in the back of your book, it has the density and the unit weight of seawater. And I think whereas normal fresh water is around 9790 newtons per meter cubed for room temperature water, seawater, because it has salt dissolved in it, its density is higher. And so is the unit weight. The unit weight of seawater, I think, is around 10,200 newtons per meter cubed. And so if you have a problem, for example, a problem due on Thursday of next week that mentions the ocean or seawater, then what you'll need to do for that hypothetical problem is look up the unit weight in the back of your book to find out the gamma that applies. So delta P just talks about a change in pressure as you change the depth. And remember, our original formula of the hydrostatic equation had this negative sign. So the negative sign in this formula tells us that as you go down through a fluid, the pressure increases. As you go up through a fluid, the pressure decreases. And so this abbreviated formula, we have to apply the same trend. If you go down through a fluid, the pressure goes up. So here's that Challenger Deep again. If we have 10,911 meters and a gamma for the seawater is 10,100 newtons per meter cubed, then what's the pressure change to the bottom? So we're talking about the pressure change from the surface of the ocean to the bottom of the ocean. And this is a gauge pressure. You know, the way that this language is written, it implies that what we're finding is the pressure in gauge terms. But really, it's just talking about the change between the surface and the bottom. And so you would solve this one. I'll get my calculator handy too. So it is the delta H, which is 10,911 multiplied by 10,100. And the pressure is going to be, oh, I wish my calculator put commas in because this is a big number. It looks like 110 million. So 110 megapascals at the bottom of the ocean with the seawater as the unit weight. And so it's 110 megapascals higher pressure than it is at the surface. All right, earlier there was a question, what if it's two different liquids? What if you have two different kinds of liquid because they're not going to have the same unit weight? What do we do there? Well, this is that very case. You apply the hydrostatic equation in steps, and the pressure is additive. So let's say, for instance, that we have oil, a layer of oil floating on top of a layer of water. And as the problem statement says here, we have a specific gravity, Sg, of the oil is 0.75. And then below that is water. And we want to know what's the gauge pressure at the bottom of the tank. So gauge pressure means assume that the pressure at the surface is 0. So assume that the pressure of the air and the water at the surface are the same. Actually, it's oil. So the liquid pressure at the surface is the same as the air pressure. So we're using our atmosphere as the 0 point. We want to go down through the fluid and find out what is the pressure at the bottom. Now be cautious here. It says that the total level of liquid in the tank is 4 meters. So be cautious about how you dimension this. My suggestion is that, let's see, I don't think I have it dimensioned. All right. So if you have this printed out, sketch, or if I don't have it printed, if you don't have it printed out, you can just write it on a scratch piece of paper. Write the dimensions, like the thickness of the liquid layers, directly onto the sketch. And then try and find out the delta P. What's the pressure at the bottom of the tank? You have to do it in steps. First, find the pressure change through the oil, then find the pressure change through the water, and then the total pressure change is the sum of those two. So the steps here is, first of all, find the pressure at the surface, so that's 0. Then find the pressure at the interface of the oil and the water. So for that, you're going to have the delta H is 1.1 meter, and the gamma is going to be 0.75 times 9810 newtons per meter cubed. So let me show you what that looks like. All right. So you can see I did this preliminary work at the beginning. I found the unit weight of the oil just because I know I'm going to need it. So the unit weight of the water is 9810 newtons per meter cubed. And then the unit weight of the oil is 0.75 times that, because the problem statement told me what's the specific gravity of the fluid. So the specific weight is specific gravity times the specific weight of water. Now, did you get the dimensioning correctly? If the total column of water height is 4 meters and the oil layer is 1.1, then that means that the water layer is 2.9 meters. That's sometimes a stumbling block. If you don't pay special attention to the description of the layers, you may accidentally think that the water layer is 4 meters, but it's not. It's saying that the total liquid level is 4 meters. So that's where these dimensions come from. So now I'm progressive. I start at the top, and I know that the pressure at location 1 is 0. So you'll notice here I've put the labels location 1, location 2, location 3, and those spots correspond to an interface. So the first location 1 is at the interface of air and oil. Location 2 is the interface of oil and water. Location 3 is the interface of water and steel tank. So if the pressure at 1 is 0, then the pressure at 2 is going to be however much pressure there was at 1 plus the change. And since we're going down from 1 to 2, then it's an addition. So we add the pressure change. And the pressure change in that first segment of 1.1 meters of oil is an increase of 8093 newtons per meter squared. So that's how much the pressure goes up in the first layer. And now the pressure at location 3 is going to be however much pressure there was at 2 plus the change. And so the change is the delta H from location 2 to 3, so that's 2.9 meters, going downward through the water, and so we use the water gamma, not the oil gamma. This time, between 2 and 3, we're passing through a liquid layer of water, so that's why we use the unit weight for water. So in the end, the final pressure is 36,542 pascals. Here's the entire look of that problem. Any questions about this example? Okay. Well, let's make things interesting. That was 2 liquids. What if we make it 3 liquids? Let's say, for example, that we have a layer of oil, and there's a layer of water, and then a layer of some unknown fluid. We can use the hydrostatic equation to find out what's the unit weight of that unknown fluid, because we have measured a known pressure. So what this problem is saying is we know the pressure at this location. At a certain location that is 0.8 meters lower than the interface, the pressure is 45 kilopascals, and that's the gauge pressure. What we want to find is solve for gamma. And so your process, what you're going to do is the same thing I did in my example where I had like location. You remember how I labeled it? Location 1, location 2, location 3. Do the same thing on this next problem. Try and identify different locations. The way that I did it was I called location 0, location 1, location 2, and then location 3 is at the elevation of that known pressure. So what I'm going to do is I'm going to pause for a moment. What we're trying to do is solve for gamma. Find the specific weight of this unknown purple fluid. Okay, so here's 3 fluids. And this first sketch is just kind of a summary of what we already have from the problem statement. But we're going to do this in steps. Starting off with the pressure of the air is 0 gauge pressure. And so I'm calling it location 0 is the interface of the air and the oil. So the pressure at location 1 is going to be the initial air pressure plus the change. So 0 was our gauge pressure at the interface of the air and the oil, and then we increase because we're going down through the fluid. So down through 0.5 meters of the specific gravity is 0.78, and that's multiplied by 9810, which is the unit weight of water. So here you can see I've got this intermediate thing written. That's the gamma for the oil, 7651.8 newtons per meter cubed. And so if you add the 0 air pressure to the change, then it is 3,825.9 newtons per meter squared at location 1. And then now we just go down again through another segment of the fluid. So now we go down through from 1 to 2, and we're going down through, it says here that the density is 999 kilograms per cubic meter. So to use that given density, we have to multiply it by G in order to get gamma. Remember, gamma is density times G. So the unit weight of this fluid between 1 and 2 is 9800 newtons per meter cubed. And so if you go down 1.55 meters of that, we now have the pressure at location 2 specified. The pressure at location 2 is 19,016 pascals. All right, so we started off by knowing the pressure at 3. That was in the given. The pressure at 3 is 45 kilopascals. So far we've calculated, we know the pressure at this layer, at the interface between the water and whatever this purple stuff is. So just from the calculations so far, we can see that that is 19,016. And so P2 is 19,016 newtons per meter squared, and then P3 is 45 kilopascals. So here's our hydrostatic equation. We don't know gamma, but we do know delta H. Delta H is 0.8 meters, and the delta P we're going to get as it's the difference between 45,000 and 19,000. And then the only unknown will be the gamma. So it's an equation with 3 variables, 2 of which are defined. So rearranging to find the, let me zoom out a little bit more so you can see that in context. Okay, so the delta P that's going to go into our hydrostatic equation is the pressure change between location 2 and location 3. So the change in pressure is essentially 26 kilopascals. Here's the change in pressure divided by the gamma, divided by the delta H, then that enables us to calculate the gamma. And I think you have a homework problem similar to this where you are determining the unit weight based on a pressure change you could determine and elevation change that you can measure. Does this make sense to everybody? Do you have any questions about what we've done? Instead of finding the unknown pressure, we've measured the pressure and solved for what unit weight must have caused that change in pressure. Any questions? All right. Well, that's it for today. Remember that what you can begin doing is looking at homework 2. And so if I pull that up on Blackboard, I'm not sure if I can. Oh, okay. Looks like maybe I can. Briefly look over the homework to see what we've got on this one. So the assignment reminds you that it needs to be a single black and white PDF file submitted by 11 o'clock on Thursday, the 10th of September. So we've got a vapor pressure problem for problem 1, another problem related to vapor pressure and boiling for problem 2. Problem 3 is about the hydrostatic equation. Some of the rest of this pressure transmission. So starting on problem 4, we'll get to that in Tuesday's class. But so problems 4 and 5 you can do after next week on Tuesday. But you can solve this problem 6. This is very similar to what we've just done, where you're applying the hydrostatic pressure through several different fluids. Problem 7 is hydrostatic pressure. Problem 8 you can't do yet. We're going to do that on learn that stuff on Tuesday with pressure transmission. But about half the problems you're able to get an early start on if you want a little extra fun over the weekend. All right. Well, that's it for today. Get in touch if you have any questions. Otherwise, I hope you have a nice Labor Day. You know, remember Monday is a holiday, but fortunately our class is on Tuesday, so we won't be missing any learning opportunities due to the holiday. So,
will homework solutions be posted?
They will not, but the grader will give you guidance when scoring your work. You know, if you miss a certain problem, the grader will indicate how many points you missed on that problem and also give you an idea of what you did wrong. And so if you can't figure out maybe what you've made a mistake on and you want additional guidance, you can get in touch with me and I'll go over it with you. I can show you the solution, but I don't post it as a PDF. All right, take care, everybody. Thank you.